the part on HDL code verification, HDL code generation. We'll visit a little bit what we can also offer you on terms of SoC design, right? So like I always do, what I always do is like to compare what the conventional FPGA development workflow to what we can provide today. So to start, we can consider this very simplified, abstracted FPGA SoC development workflow. So this workflow is focused on development of, let's say, new algorithmic content. So the algorithm development is done based on a set of course, functional requirements, and the algorithm developer performs later on a behavior model. So it reminds us, of course, on the HDL workflow, conventional workflow that we saw during the HDL coder presentation. So later on in the SoC development workflow, system designers usually divide the algorithm into hardware and software partitions based on, of course, their experience and their company practice. The choice, of course, it will be aided by simulation, usually, and the software and hardware partitions are handed off to either embedded software design teams or the hardware design team. But before coding start, we need actually we have some refinements for the algorithm that is needed for the algorithm. For example, we have some behavior models. Often, for example, we usually for behavioral models we often use frame-based instead of like sample-based. But hardware design will require, for example, introduction of streaming architectures. Like we said, floating point algorithms are converted to fixed point for efficiency and so forth. So only after this work is complete between the software development team and the hardware development team that we can start going into prototyping, or we can start targeting our FPGA or our board. So this classical or conventional workflow, we see that the hardware and software paths don't come together till the FPGA prototyping phase, right? So it can be and debugging on the FPGA directly, it could be very challenging, especially if we don't have some common grounds for debugging or for a software and a hardware simulation. That's why with SoC block set, we believe that Simulink models could incorporate the effects of the hardware and software architecture very early in the process and along with the algorithm, right? So through simulation design, both teams can start evaluating hardware and software at the model level in Simulink. So before going to the FPGA and the SoC development force. And in this case, simulation will provide visibility into timing effects, for example, that can be very challenging to directly detect in hardware. So then they can, of course, progress into hardware synthesis and building software application. They will use FPGA prototyping at the end, but in that case, SoC block set will provide an automation to build an automation workflow or automated workflow to build complete hardware and software applications and deploy them on the FPGA and the SoC boards. So ultimately, what we are trying to do is to create a virtual platform and introduce or integrate the production platform, which is the custom FPGA board. So we are creating a virtual platform that will combine all the effects that both of these partition will have on each other, but we will also see the effect that other parts will be having also on the software and on the hardware parts. So if we go back to a classic model-based design workflow, so we'll be having an algorithm 1 that maybe it would be HDL or hardware, and algorithm 2 will be more on the software part. We'll be having the algorithmic model. We'll go through code generation to go through algorithmic code, and later on we'll be having the hardware implementation. And using model-based design, you can generate this code for both hardware and software, of course. using HDL and embedded coder. And this code is included in the reference design that you will be having. So this reference design is either provided with MathWorks via the hardware support packages, but you can also use your own or import your own reference design into the platform. So, and you can notice that various aspects of the hardware, like memory, interconnect, external IOs, are not represented in Simulink. So even if with the model-based approach that we went through at the beginning, and we said, okay, we are trying to combine everything and simulate everything in Simulink, even with that, if we are deploying on hardware, we are missing some of the aspect of the simulation. We are missing some the representation of some aspect of the board, like the memory, the interconnect, the external IOs. And which means that we are only validating the algorithmic aspect of our algorithm, but not the complete implementation of our algorithm on the board. So this often also leads to some issues that are detected after the implementation, and leading also, of course, to the difficulty in debugging on hardware. So what we are trying to have with SOC block set, like I said, it's a virtual platform in Simulink. We are having a more efficient way of validating and testing our code with all the peripherals or the hardware components that could come into play before going to the hardware itself. So if we go and take a very simple example, like data exchange between FPGA and the processor, or let's say the ARC processor here, we can see that there's a complexity related to the data exchange between algorithm 1 that is deployed on hardware and the algorithm 2 that is implemented on ARM processor, and the data is moved usually through FIFOs and shared DDR memories. And since the two systems, FPGA and the processor or the ARM processor, are completely asynchronous, designing this data path usually is very challenging. So we have to decide on variety of design parameters, like, for example, the other memory readers and writers. If we needed, we need to see the data rate, the FIFO size in the FPGA part, how to synchronize incoming data with task execution on the processor side, how many buffers do we need in the memory, and so on. So what we are trying to here to resolve here is or to prevent the contentions that could have on the memory and the ARM processor part. And the solution that we can provide with SOC block set is rather not only, for example, here we have always the FPGA or hardware logic part and the software logic part. And what we are trying to resolve is the lack of the representation of all the hardware components. So with SOC block set, you can model the interfaces between the software and the hardware and decide on these parameters. Okay, and this allows you to detect, of course, the problem in software rather later, or software like I say in simulation, rather than later in the implementation. So you can simulate here in this example the memories, the hardware-software interfaces, which is a memory and registers interface, and of course include the external input and output, and the test benches later on the output. So if you go back to our example, we will not only see this time algorithm 1, algorithm 2, but rather we'll be generating code for algorithm 1, algorithm 2, not of course for the input output and the memory channel, but our code will be mapped directly through our reference design. So we'll simulate the algorithm as well as the hardware software architecture. So we'll go through memory, task scheduling, IOs, and external connectivities. We can later on, like I said, deploy on supported hardware through code generation, and the code will be mapped through the reference design, always through the reference design on the hardware. And we can, what's also very interesting with SOC block set is that we could have also some profiling we can profile the performance of the deployed design using the external mode. Okay, so we can to sum the SOC block set is that we can go from a very exhaustive hardware, virtual implementation of our model through the real implementation of our design through simulation. So we can start with simulating hardware architectures with the algorithm. Later on, we can deploy directly on the boards. And finally, we can profile the software performance, for example, or the hardware utilization on the hardware devices using the external mode. So we have a great material for getting started with SOC block set. So we have some examples just to get you started. It will be based on the examples that I showed you for streaming data from hardware to software, but you can also find how to, for example, use, you have some very application-oriented examples, and you can see how also we can do some profiling to assess the software performance on CPU using the external mode. So just I'm repeating this, but I think it's very important. Don't hesitate to check our documentations. It's public. Even if you don't have access today for SOC block set, you will have access to the explanation, the visualization of all our examples and blocks and workflows. To sum up my presentation, and I hope that I have answered your questions, or at least some of your questions about how we can leverage MathWorks tools for design and verification. So going from a high-level design with the model-based approach, going to the code generation, specifically HDL code generation. Later on, how we can leverage also code generation for some specific application like DSP, or digital signal processing and wireless communication, and how we can also verify our design and our code, how we can integrate our design later on our platforms, and finally, how you can use SOC block set to integrate and partition the software and hardware part and create our virtual platform directly in Simulink before going to hardware.